to the webinar Data Analysis with OptiSlang. The webinar is organized as follows. After a short introduction to OptiSlang, we will have a look how we can import external data to the OptiSlang post-processing. Then we will perform sensitivity analysis and an optimization on the external data. Finally, we will discuss an interesting application, and then I will present the OptiSlang training program. The webinar is organized as follows. I will give a presentation of about 40 minutes, and then we have time for discussion. You can use the chat window and the question and answer window in the WebEx environment to type your questions, and I will answer it in the discussion. Let us come to an introduction to OptiSlang. Renato develops OptiSlang and several other software tools like Statistical Structures and Multiplot. Was founded in 2001 and has already 50 employees at Weimar and Vienna offices. We are developing mainly software for sensitivity analysis, optimization, robustness analysis, evaluation, robust design optimization. On the other hand, half of our team are consulting engineers working with the software on real industrial consulting projects. The idea behind OptiSlang is that's an algorithmic toolbox for sensitivity analysis, optimization, robustness and reliability analysis, and it should offer the functionality of optimization and stochastic analysis to real-world applications. It has defined workflows, wizards, robust default settings that the engineer can use it without deeper knowledge of the algorithmic background. If you now want to talk about the special topic of analyzing external data, this means data which are not generated by OptiSlang with some solver, but with some measurements maybe or some other calculations, we can use this the sensitivity analysis as well. We can perform univariate and multivariate statistics, and with help of the sensitivity analysis, we are able to quantify the influence, the sensitivities of the input parameters with respect to the important responses. We can estimate the variation of the responses. We may estimate the noise or the error in experimental measurements, and overall the sensitivity analysis gives us a better understanding and may be used to verify the dependencies between input and output variations. So before we get started with the statistical analysis, we need to transfer the data from your data set to OptiSlang. So if you have external data, then we can import them from Excel via Excel add-in. This I will show during this webinar today. We can also import comma-separated files, and we have also possibility to run Python interface. Most simple way is the Excel add-in I will show. We can also then export data from statistical analysis, sensitivity measures, and so on to Excel or text files. We can also print out or export the plots in the statistical evaluations and the tables. So we have an external DOE. We will use the Excel plugin, and then we will perform sensitivity analysis based on this data. The Excel plugin is a simple tool which is available without any license, which can be used to export data available in an Excel sheet directly to an OptiSlang binary format. So I will show this by means of this simple example. We have an analytical function having 5 input parameters and 1 response function. So I have prepared for this purpose an Excel sheet where we have 5 individual parameters within the range between -pi and +pi, and we calculate this formula in Excel, and now we want to evaluate the statistical sensitivities based on this data set. So we have generated a DOE set consisting of 100 samples. Somewhere might be measurements, might be some external design of experiments, and then we obtained the corresponding function values. After installing the Excel add-in, you will find it in the tabular add-in. You will find this button Excel Export, OptiSlang Export. If you press this button, then you are asked to select the data for the input parameters, for the input values. So you can just select the raw data, but you can also select data including parameter names if they are available. And then the add-in detects 5 parameters with 100 samples, so you can decide if you have horizontal layout, so if each row is one design or if each column is one design. We have detected 5 parameters with the names x1 to x5. The next step, we do the same with the output values. We have detected 1 output value with 100 designs. Then we have the possibility that we can give the individual samples also individual numbers, or we can just use a continuous design enumeration. So in this case, I keep this continuous design enumeration, and I will finish this export by writing an OptiSlang binary file. Then the export is finished, and we find a binary file in our folder. We can now open this binary file directly, and we will see the statistical data of the statistic processing. Here we get the 100 samples, 5 input parameters, 1 output parameter. So this was the export, how it works with the Excel add-in. So quite easy. If you have data available in an Excel sheet, you can export it simply to OptiSlang binary format. Now let us discuss how we can perform a sensitivity analysis. Before we have to make some notations. Input variables are defined with capital X in the following, output variables with capital Y. We have input parameters which are mainly some kind of design parameters. We can apply sensitivity analysis for numerical models, analytical models, or even experimental results. If there is no simulation available, we can directly measure the design of experiments with experiments as well, and then we can evaluate different response values out of these different designs. So what possibilities are available for a statistical evaluation? The first one are so-called Untitled plots. This is a pairwise plot between one input variable and one output variable. This looks quite nice if we have a linear dependence or an additive nonlinear dependence. we can just see a qualitative representation of one-dimensional dependencies, linear and nonlinear. But if the dependence becomes more complex, if there is interaction between the individual variables, like here on the left, having a multiplication, then you see that this entropy plot maybe not, or just quantification of the variable importance maybe not as easy as for additive dependence. If you have nonlinear interactions and even an overlapping of additive and interaction parts, then you might imagine that it might become quite difficult to estimate the influence of the individual input parameters. So we need some measure for the quantification. One state-of-the-art measure is the coefficients of correlation. It quantifies the linear dependence between a single input variable and a single output, or may be also used to quantify input and input, or output and output. So it's a covariance divided by the standard deviations of the two variables. This coefficient of correlation is always between -1 and 1, and it's the degree of linear dependence, and it cannot quantify any interaction. So if you go back to this types of interactions, where we have bilinear and nonlinear interactions, then the coefficients of correlation will just estimate zero influence of this variable to the response y. The coefficients of correlations are collected and obviously in post-processing in a correlation matrix, which is a symmetric matrix. We can have a look now on this data we obtained from the Excel export. So this is the statistic post-processing of Optislang. On the left-hand side, we see linear correlations. Left bottom, we see quadratic correlations. In the middle, we see the entry plots and corresponding histograms of two variables. If I now click somewhere into the correlation matrix, then the corresponding entry plots and histograms are adapted. For example, I want to see how is the influence of x1 over y. Only see it might be quite difficult to estimate some of the dependence. We can select a one-dimensional regression analysis in the entry plot. So you see here a linear regression line with respect to one input parameter. The same with parameter 2, there we see a bit larger correlation coefficients is indicated here in the title line. So it's 0.4 for this variable x2, and it's 0.2 for the variable x1. For the third variable, it seems to be a bit larger due to the sign term. We can remark this sign term in the entry plot as well. For the other two variables, we see almost no correlation in the entry plots. If you plot on the diagonal of a variable, then you see always correlation of one variable over itself is 100% correlated. So if you click on the diagonal, then we see here an ordering of linear coefficients of correlation with respect to this single response value. And we see that the largest coefficient of correlation is x2 and then x1. Yeah, but it might be quite difficult to decide, is this estimate for a linear coefficient of correlation sufficient? If there are nonlinear dependencies or interactions, this might be difficult. One nice feature also available in post-processing, statistic post-processing, is the so-called extended correlation matrix. Since the linear correlation matrix is symmetric, we need just to show one half of this matrix, and on the other half we see the corresponding antiplots in one plot. Since the diagonal is always 1, we see the corresponding histograms. Here we see that the input parameters x1 to x5 are uniformly distributed, and the response y is somehow not uniformly distributed. So the linear correlations or the one-dimensional measures are limited to one-to-one relations. We cannot represent interactions, and we have no idea if the linear correlation coefficient is around 0 or is quite small, if there is no dependence or if there is a nonlinear dependence. In order to overcome this limitation, we have developed several approaches based on the response surface method. All of them are restricted to a specific number of input parameters. Since with increasing dimension, the approximation quality decreases. In order to apply the response surface method, where the real solver response or the experimental results are represented by some regression function, we have several mathematical models available, for example, for regression, neural networks, and others. But the question is, which one is the best for this specific situation? So we need an objective measure for the prognosis quality. We have developed an algorithm called the so-called meta-model of optimal prognosis, which automatically finds the optimal approximation model, which it will detect the parameter subset of the important variables. This enables to apply this response surface approach up to a large number of parameters. And based on this approximation function, then we will get the individual parameter influences by variance-based sensitivity analysis, which are then shown in the post-processing. In order to perform such an MOP, we have to leave the standard post-processing and run this algorithm. If we go to OptiSlang, we have an empty scenery. We can directly take the PMOP node. This is the new version of the meta-model of optimal prognosis. We can open the node and simply import now the binary file, which was created with OptiSlang Excel add-in. Now we see that this node automatically detected 5 input parameters and 1 response. We can decide which models have to be checked. So in our case, we have enough data for these 5 variables. So we will check global models like polynomials and also local models like moving least-squares and kriging. So this is the only things we have to do. Then we can execute the project, and then the MOP algorithm will automatically detect the best approximation model. We can have a look on the results. So we see what approximation quality could be obtained with linear regression in moving least-squares and kriging, and you see that here the highest approximation quality could be obtained with kriging. And now we can enter this MOP post-processing. Then we will get a 3D surface view of the subspace of the two most important parameters. So we see here the response with respect to x2 and x3, which are the two most important parameters. We can switch to another subset here, x1 over x2, and you see the approximation function together with the designs we have taken from Excel sheets. So with help of this automatic approach, we can directly build up a mathematical surrogate function which is suitable to approximate the external data. In our case, we have 97% coefficient of prognosis, so the approximation quality is excellent, and we can go further with this mathematical surrogate function to make some search for some optimal points. So instead of having a real simulation model, you can use experimental data also to perform an optimization. You need to perform experimental design of experiments, and then based on this mathematical approximation function, we can then directly perform an optimization. This brings us to our next point. Before we go for the optimization, just a summary about the sensitivity methods. So the correlations can be computed quite easily, and they are one-dimensional linear quadratic dependencies. They have no error measure, so we don't know if this assumption of linear or quadratic dependence is useful or not, and they can handle inputs which are independent and maybe even dependent. The MOP-COP approach is a multidimensional multivariate analysis which will identify nonlinear dependencies by automatic choice of the input parameters. We have the coefficient of prognosis as error measure, so we will estimate how good is the approximation quality with respect to unknown data, not only the goodness of it. And it can represent, or the sensitivity measures are suitable for independent, weakly correlated input parameters. So the sensitivity analysis based on external data is nothing else than the procedure I've shown to you. We have the external DOE, the Excel plugin, and then the MOP, meta model of optimal prognosis. And the results on our test function we have already discussed. We have three important parameters. Two parameters are not necessary to represent the response function in this example. So let us come to the optimization. We want now to perform an optimization on the approximation model. So we have the external DOE data. We have generated an approximation model based on the MOP, and now we can run an optimizer directly on this approximation. So we need to define criteria. We need to choose an optimizer. OptiSlang has several optimizers available: gradient-based methods, adaptive response surfaces, and natural-inspired optimization. So the optimization wizard will help us to choose automatically an optimal method. Before we have to define objective function, constraint functions. They can be defined with respect to the input parameters and the response values available from the DOE data. So if we have a smooth approximation function, which is the case if we apply the MOP approach, then usually we can estimate gradients quite well. So the nonlinear or the gradient-based optimizer might be the best choice. We have to take care that this optimizer may run into a local optima, so we have to choose a good start design in order to run to the global optima. So I will present this, how this works. If we have generated our meta model of optimal prognosis from the external data. Then we can apply the optimization wizard on this meta model. We can define lower and upper bounds. Here the bounds are automatically taken from the range of the samples available in the data. Two parameters, x4 and x5, are not available for optimization since they are not used in the meta model, they are filtered. We can define an objective function and a constraint function if you like. And then the wizard automatically just suggests the gradient-based method. So if we start with the gradient-based method somewhere, so if you don't specify a start value, then the reference point is taken, I think, from the first design from the external data. So it might be the case that the local gradient-based search may run into a local minima. So we have to choose a start design from the binary data. Later, we can keep the settings of the optimizer, and yeah, we can keep also the settings for the post-processing. We cannot validate the best design since we have no solver. We may validate the best design afterwards with some new experiment. So the solver chain looks the workflow looks something like this. Based on the meta model, we started the gradient-based NLPQL, which uses, instead of a real solver or a real simulation model, uses the surrogate solver, the so-called MOP solver, evaluating the approximation function. Then we get the optimal value. Now we have also to select the start design. This is possible if we double-click on the NLPQL system. In our case, we cannot import the start design from other systems since we do not have any sensitivity study available in here. So we have to import the start design from a result file. This is the binary file from the Excel add-in. Then we get a table of all the designs. We can sort with respect to Y, and I take here the design having the lowest value for Y. And then I can start the optimizer. It will converge in a few steps. So there are 1, 2, 3, 4, 5, 6 iterations, and it will converge to a value of -11. If you look to the corresponding function. So the optimizer started somewhere here, and it converged to this region where we have the minimum value of x2. We have the maximum value of x1, and x3 is something around the -1.5. So here the minimum of this function was found by the optimizer. So with help of this procedure, you may also use experimental data for an optimization. If you are satisfied with the optimum found here, you can proceed with an experimental validation, and we have the possibility then to extend the data in the next step and do the procedure again. Yeah, so you need to build up first MOP approximation model with help of the MOP node, and then you can apply an optimizer also on the MOP, and you can update the data in your external DOE and do the whole procedure again if you have added some new experiments or measurements at the specific parameter combination suggested by the optimizer. So let us come to some application example where I investigated real measurement data. It was medical study in the United States where 250 men has been investigated in order to find a good way to estimate the body fat content or the density with respect to some body measures. Since the body mass index does not represent if the body contains mainly of muscles or contains more or has a higher fat content. So the question was, is there a possibility to derive some correlation, some dependence between measures like abdomen, like chest and so on with respect to the density. Here again we have an Excel sheet with the data. We can export the data. I will show you the Excel sheet which was available from this research group. So we have 11 measures like the height, neck, chest, abdomen, hip, and so on. We have the weight of this person and we have the age. And we want now to estimate the density, which was measured in a quite complicated procedure. And from this density, then several measures are derived and compared to the body mass index. So we are concentrating mainly on the density. If we export this data, then we will see that the input correlations have high values. So it's clear if there is some higher weight, then usually the hip measure, abdomen, and so on, they will increase. So the exported data look like this. We have 12 input parameters and 5 response values. We concentrate now on the density. All the others are derived values. We see that there is a high correlation between the neck, chest, abdomen, and so on measures. And first we have to check the data, and it can be seen that in the column of the ankle there are some data which might be not useful. So if we go to the ankle plots, and you see that this is the ankle or the cloud of the data, and here are 2 points which may be some outliers, so we can color them and check them in the other ankle plots, and you see that they are always quite large ankle values, so we can decide that these 2 may be some outliers, so we can deactivate them. On the other hand, we may check the data further. For example, if we have a look on the abdomen and the density, then we see there is possible this one far away, so we have large abdomen, but we do not, but with a high density indicating a large muscle content. So we can also, if we have check this, we can also deselect this as an outlier. So if you have deselect outliers, we can save the data set as reduced data set, which can then be used for further investigations. Interesting in this example is also the correlation between the density and the body mass index. So we have some correlation, but it can be explained just with about 50% the variance. You see there's also some scatter. So the body mass index and the density, this was expected, are not highly correlated. And if we look, for example, on these two values where we have a high body mass index and a small density, and if you look now what is height and weight for this example, these are the two inputs for the body mass index, and you see that these are two people having a quite high weight compared to their height. Yeah? So these two may be also somewhere outside the cloud, but we will keep them in the analysis. So the next step will be that we will perform the MOP analysis. So we enter the MOP node. We open the data set here. I've taken the reduced data set without the outliers. We have these 13 input parameters and the 5 response values. Since the input parameters are correlated quite highly, I have deselected moving these graphs increasing because they don't perform very well if you have small number of data and if you have highly correlated input parameters. So what is the outcome of this analysis with the MOP? We see that the density is mainly influenced by the weight and by the abdomen, and it can be explained with 73%. Yeah, we can explain 73% of the density now, which is much higher than with the body mass index. But we see that if you look on the input correlations, that the abdomen and the weight is highly correlated. So it might be also possible that the measure abdomen might be too strongly correlated to the weight, that we have mainly weighted to heavy people. So it's better always if we can explain the response values with not as highly correlated parameters as we see here. For this purpose, we have developed some input correlation filter, which helps us to automatically deselect highly correlated input parameters. So you will find this in the part of the filters. So there's an input correlation filter. It will eliminate input correlations larger default settings than 0.7. So in our case, if we take this filter, then we will get a different input parameter set, which can explain the density again with 73%, which is then the abdomen, the wrist, and the age. And then these three input parameters can explain the density with the same quality, the same prognosis quality, but with less input correlations. Therefore, this approach might be more stable. So this was the procedure I wanted to present to you, how you can get external data to the OptiSlang post-processing and how to perform MOP and optimization on this external data, which may be optimization, maybe an experiment or some other evaluations. Some comments to our training program. We have an introduction, 3-day basic training. We have 2 days inside ANSYS workbench introduction. We have an one day advanced training for OptiSlang and ANSYS Workbench, one day parameter identification, and also one day robust design and reliability analysis. So if you are interested in further information and the trainings, please visit our homepage. You will find also the video and the slides of this webinar there soon. Thank you for your attention, and I want just to give a comment on our Weimar Optimization Stochastic Days taking place in November each year, where the users worldwide meet in Weimar to discuss about their applications. So